You deploy an LLM agent to handle a complex, multi-step task. For the first few steps, it works. Then it forgets what it just tried, repeats a failing edit, and the entire run collapses. This collapse manifests in 3 specific symptoms. First, context drift, where a hallucination at step K corrupts the data carried into step K+1. Second, infinite repair loops, where the agent trusts its own output and cycles endlessly on a single broken task. Finally, runaway token cost, as the budget scales without the system ever converging on a solution. These symptoms are the direct result of relying on prompt-isolated execution. When an agent runs on isolated prompts, it operates with no persistent state, no durable record of past actions, and no formal verification mechanism. Upgrading to a stronger model masks these issues temporarily, but the structure guarantees they return. Agentic collapse stems from architectural software failure, not a limitation of the LLM's raw reasoning. The fix requires a shift in discipline to loop engineering. Instead of tweaking prompt instructions, we design a closed control loop. Inside this loop, the LLM is restricted. It acts solely as an action planner inside a deterministic software structure. The model proposes an action. The structure decides if it executes. The operational blueprint for this closed-loop system is LEAF, the loop-engineered Agentic Framework. LEAF divides the agent into 4 decoupled subsystems, each designed to systematically solve one of the failure modes we just identified. This framework replaces conversational prompt fragility with rigorous deterministic software. It consists of a loop controller, a Task Verifier Engine, a durable state spine, and a Memory Maturity Subsystem. Equation 1 defines the baseline agent loop. It shows the loop state at iteration k passing through a transition function, t. The new state, sk+1, is calculated based on the previous state, the action taken, the observation, and the verification outcome. This transition function forces the preservation of an immutable history. The static context variables carry forward completely unchanged, while new events lock into place sequentially behind them. This mathematical state preservation directly addresses the first symptom, context drift. Because the history is preserved exactly as it occurred, a bad model output cannot rewrite the past. LEAF implements this state preservation physically through the durable state spine. This is a transactional append-only register. Every action, observation, and verification verdict is recorded here in a linear sequence. This register enforces a crucial operational rule. An action failure is not a loop failure. When a proposed action is rejected by the environment, the system does not roll back or abort. It appends a failure event to the log and increments a retry counter. Standard open-loop agents lack this discipline. When they fail, their ephemeral working memory is corrupted, erasing the context of what went wrong. By maintaining a durable spine, the agent treats the rejected action as new evidence. The explicit failure becomes part of the context for the next iteration, allowing the model to adapt its strategy. That brings us to the second symptom, infinite repair loops on tasks that possess a single, objective, correct answer. The structural solution is the Task Verifier Engine. It removes the agent's ability to verify its own logic. Equation 2 models this as a deterministic binary gate. An action is paired with a verifier function that runs against the real environment. If the verifier returns a 1, the state evolves. If it returns a 0, the action is rejected before it can mutate the global state. The ablation data for this component is explicit. When researchers removed these automatic verifiers during complex code refactoring tasks, precision dropped from 89% down to 54%. These numbers confirm that self-correction without objective external feedback is operationally insufficient for complex tasks. An external deterministic gate is mandatory for reliable performance. The final major symptom is runaway token processing costs, which compound rapidly on long-running tasks. This cost is governed by a strict physical constraint inside LLM infrastructure, key-value cache invalidation. If you place volatile or frequently changing data near the top of the prompt, every single update invalidates the cache tokens of everything downstream. To bypass this compute penalty, LEAF enforces a strict 3-region context layout rule. Region 1 is the static head. It contains immutable system instructions and role specifications that never change. Region 2 is the append-only history. This is the durable state spine, rendered directly into the middle of the prompt. It only grows at the end. Region 3 is the dynamic tail. All volatile, frequently reevaluated state variables sit at the absolute end of the context string. This chart maps standard attention compute cost over time. Without a strict layout, attention mechanisms scale quadratically. As the prompt history grows, the cost to process each step multiplies exponentially. By locking the dynamic region to the tail, the entire prefix remains pre-computed in the KV cache. Equation 3 demonstrates per-step attention complexity dropping to a linear scale relative to that prefix. The system computes heavy static and history blocks once and reuses them. Breaking this specific layout rule carries an immediate physical cost. Testing shows a 3.4 times token recompute penalty the moment dynamic data is misplaced at the head of the prompt. Prompt topology acts as the primary lever for controlling and surviving agent execution costs. Even with an optimized cache, there is a physical limitation. An append-only history will eventually exceed the model's maximum context window limit. To prevent tasks spanning days or weeks from crashing, Leaf introduces the Memory Maturity Subsystem. This system manages a 4-tier hierarchical progression. It moves from L0, the raw, volatile context window, up through ephemeral event logs and local files, all the way to L3, highly distilled, compacted knowledge banks. When history exceeds the context threshold, a compaction operator activates. It extracts older, bloated blocks of history from the lower levels and moves them up into the L3 bank. This compaction runs on a strict loss function. It minimizes semantic discrepancy while applying a heavy penalty for the accidental deletion of any unresolved open tasks or to-dos. By physically separating the ephemeral per-step logs from the cumulative knowledge banks, the agent can run theoretically infinite loops without suffering from systemic amnesia. When assembled, these 4 subsystems form the complete Leaf data flow. A task enters the controller, which renders a prompt, receives an action from the LLM, passes it to the verifier, appends the result to the spine, and updates memory. This is Table 1, comparing Leaf against open-loop industry frameworks like React or LangGraph. Leaf is the only framework on the board that explicitly mandates both an execution guarantee through verifier pairs and guaranteed KV cache reuse. This architecture does carry a specific operational trade-off. Forcing a deterministic verification on every single step imposes an average latency tax of 15 to 30%. It also introduces an open engineering challenge, automatically synthesizing rigid verifiers for ambiguous tasks like research or design, where formal test schemas do not easily exist. But trading raw model speed for absolute structural determinism is the necessary engineering price for deploying reliable autonomous systems. There are 3 core engineering takeaways here. First, an agent is a state machine, not a response function. The LLM must be restricted to merely proposing actions inside the loop. Second, the 3-region context layout is your primary compute lever, and the append-only spine is the undeniable source of truth for the system state. Third, every subsystem in Leaf earns its place. The ablation metrics, an 89 to 54% drop without verifiers, and a 3.4 times cost penalty without the correct layout, prove what happens when any single piece is removed. Unstructured prompt engineering has a clear ceiling. Advancing autonomous systems requires the structural discipline of control loop engineering. Reliable AI cannot be built through conversational text alone. It requires an uncompromising deterministic software architecture to hold the pieces together.